Well, hello, and welcome back to Old School Coding, where we continue working on the simulation of a 1990-ish microcomputer in C99 using the development techniques that I used back in the late 80s and early 90s. So where we left this, we were kind of in the middle of working on the simulation of the block device, that is the floppy disk controller. And I had gotten up to the point where I was pondering in my test and in my implementation how I was going to actually do the read and write. And I thought about it overnight. I thought, let's rewind back to a young Farsight and what I was actually doing in the 80s in terms of breadboarding computers and what I was seeing in terms of other microcomputers on the market and how people were approaching the problem of talking to devices out there. And there were several ways of doing this. And certainly DMA was one of them. Intel had some chips to support that, and they had some complicated mechanisms, and you would just kind of let the chip gods do what the chip gods did. It wasn't just Intel. But if you were implementing a system in discrete logic from scratch, you were designing it yourself, and if you weren't buying an off-the-shelf disk controller chip, which, by the way, a number of the chips at the time ended up having some fairly interesting errata, and they were kind of cranky, and the whole DMA concept is a bit awkward in the 8080 land. You might end up doing something like what Steve Wozniak did on the Apple II, which is minimize the hardware, do the whole thing in software. Now, I'm not going to go for full-on Woz design. I mean, goodness knows he was bit-banging the signals to the stepper motor, and he was receiving the raw data from the magnetic heads and packing it into bytes and so on. We're not going to go there because that's a really awkward thing. The back end of the simulation, so to speak, we do have a linear stream of bytes that represent the contents of a disk. And it's just the data bytes. You don't have, you see, on an actual floppy disk, there is some structure to it. Each track is divided into sectors, okay, little pie wedges. And then as you scan through the pie wedge, your head is going to, first it's going to just pick up unrecorded media. It's just a magnetic tape. Then it's going to have some sort of a sync, something that the electronics recognizes as here starts data. And then you're going to have some notation of the sector number. And then you have the data. And then there might be checksums and so on afterwards. And there are ways of encoding this, and it gets really complicated, and you've got FM and MFM and yada, 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 yada. So we're going to hide the physical reality of the disk for now. We're just going to say, once we know what piece of data from the disk we want, we're just going to get the data. But instead of having the disk controller reach back through the system and initiate memory accesses to write it into memory, what I'm going to do is instead, the CPU is going to tell the controller, seek to track, or find sector, or here's data to write, and write the sector, or here's data, here's the sector number, please, and then please read. So no more DMA. So I am going to yoink out all of the testing we've done so far. I will rework the constants as time goes by. These probably are good. First thing is that I have chased down the actual SA8, the drive that I used mostly when I was breadboarding. I had a pair of Shugart SA800s, which were very nice. I believe they did soft sectoring, which meant you basically read in the track and and it did what I mentioned. There's hard sectoring, which does something more. We're not going to get into that. It had a 8 millisecond seek time. It had some other timing constraints, but let's do a hypothetical, really fast thing. We're not going to do this busy until crap. We do want to model what track number we're on. I'm not going to do the whole thing there. What I really want to do is I want to keep track of all of my disks. So, or I could just say we have a fixed seek time. We're going to do that. So this initial disk will take a certain fixed amount of time to get to the correct track. So we do know what our current track is. But if that's going to be true, we can apply that to everyone. You know what? I'm not going to model the timing of the disk. And here's why. And this has been a thought coalescing in my head. Programs running under CP/M tended to do the following thing with the disk. They would say, read me this sector, and then they would say, I want to look at the data. So it's a synchronous operation. They would say, write this data to the disk. And when the write is done, they'd start scribbling on the buffer again. So synchronous. These are synchronous operations. So basically what you're really doing gets suspended while your call is in. Now, certain rather more advanced BIOSes might copy the data into a buffer somewhere else and then handle it in the background. I will not be writing that complicated of a BIOS, so far as I'm concerned, disk operations are synchronous. And any timing on model here is just simply sitting around and spinning our thumbs in the simulation, doing absolutely nothing for a certain number of cycles. Possibly with the CPU executing code that says check status, check status, check status. So I am going to wipe out all of this crap. So we do not have any of this. In fact, let's wipe out the test code completely for now. So dev bist impl goes away. I'm glad I didn't spend a lot of time writing comments. I think I may still need write register and read register macros. I suspect I still need that initialization for data. CTX goes away. That goes away. We're going to do bdev linked. To do test the controller. Now some of this I can keep, and some of it needs to go away. For instance, we're no longer going to have a DMA address. The control is going to be slightly different. We are likely to have to do exercise do one or more read operations. And we're going to go back to idle after that. Now, bist impl goes away. So basically we have torn out all of the code that tested the things that are going away. And I tore out too much. So I need to have a data. Oops. let's call it bdev in uppercase just to. So D becomes bdev, like that. Oh, and I had a whole bunch of these. Yeah, okay. Sec WR, oh, right, okay, so now we need, for each one of these, we need sec and, yeah, okay, DSK, TRK, and SEC, CTRL, and stat. No. So I'm not reading my error messages correctly. So I need a read and a write for each one of those three, plus a read of control and a write of a read of status and a write of control. So let's start off with so keyboard macro. Come on, close keyboard macro. Open keyboard macro, search for // tilde end of line, keep just that. So static p edge, and it's this thing underscore rd underscore is equal to bdev arrow rd of okay. So there we have our edges that we're naming. Now, as I start removing this, implementation is going to start blowing up. So notice now we're going to have 5 ports because we also need a data port. We have the system data bus, so we don't want a port called data. Let's have dat. So control status, disk track and sector number, and then a data port that we'll use to move bytes to and from the disk. Yeah, 5. And I'm just going to set this up so it happens as if we had a super hyper turbo disk. Alternately, if we had a system that simply froze until the right timing was there. Or we can presume that this is talking to a really smart controller that accepts all this stuff and does everything in memory. So when you insert a disk, it reads the whole disk and then it says, oh, I'm ready, the disk is mounted. And then we do things at target speed. And then at some point, it's going to write data back to the disk when it's done. So we're modeling some magic here. Okay, so now in the implementation, we've got all the same things. We no longer have DMA. We do have a thing at the bottom called DAT. So there's our signals. So we want to do an edge net on the edges and a data net on all the data. Let's do them just in that order. So there we've initialized our actual registers that we're storing, and the edges. Yeah. So that's not quite right. This has to have a slash here. And that is what I want it to look like. Let's try this again. Search for the equals, killed end of line. Find the blank, do that. Now edge, init, signal name, format of %s:/name without the underbar. There we go. So we can initialize all of our own stuff. This is all gone. So that WR is defined and not used. That's fine. For now, what I'm going to do is down at the bottom of dev bist, I'm just going to put voids in for these. You know what? I kind of like having BDev like that, really. And again, we have unused variables, which I'm going to tuck in at the bottom. We have invars, which went on for too far. I really am getting more and more like the idea of having that during development, because these do map back and forth. These only name it once, though. So we're going to say, yeah. So I need to stay focused. There we go. Wouldn't it be cool if that was a macro? Yeah, why not? Bdev unpack. Nope. That becomes unwieldy because I'm not naming the edges by their names. All of this going back and forth between the index into the array and the actual thing here is causing problems. So, yeah, this is going to cause us to do a whole bunch of refactoring all over the place. So we're going to write this so I can do those macros the way I was setting it up. Now the cast on the right-hand side there, that is so that when we use these macros, the compiler won't warn us about unused things. The optimizer, however, should optimize away the loads that load those up, as long as I don't have this marked as volatile. And I'm not going to do that because we don't have any other thread. So we did pdev all, which grabs all of these. Setting up so I can sneak the rest of this in together with my macros. Still don't have all of these set. There we go. Why would this not be indenting? I wonder if Emacs only... No, that's not right. There we go. And let's see if I can sneak a bit of white space in there. There we go. So now if I say bdev all, I'm going to end up with local variables that have the names of all of these guys. And let's do this first. Bdev set impl is not going to exist. We can derive our invars from these guys. There we go. And you'll notice that if I was actually working in C++, I wouldn't have to do this macro. I would have access to my member elements already. Yet another motivation for the creation of the C++ language. So now we need to hook these guys up. So we only need to keep the edges. And what we are expanding them to was things like this. Okay, so here's the name of the edge, here's the name of the thing, and here's the operation we were doing. So we're going to put that in lowercase. So now we're going to start constructing. Edge on fall of the signal, it'd be dev underscore the operation and the register like that. I hit the macro a few extra times, and because I didn't get the signal, I didn't get the register name on the end there. That's a mistake. We can fix that. There's the register. There we go. We no longer have DMA. We do have track, sector, and DAT. And we do have CTRL. We read status, and we can read DAT. Now, I would like to use my macro here, but I want the static in front of it. So what I will do is I will put that like that. Okay, so I believe that means that where we expand it, we will use the value of static. Warning, static redefined. And that's not going to work because I can't have this in the global area. Uh, okay. This is getting to be too much. Yeah, let's not. Kind of just quietly finishing up the stuff here. We do not have these guys here. We can declare them, but we cannot implement them like that. We need to implement them down here. So read status and write control. These are completely changing. Also, the data register, I believe we need to do the same thing with DAT here. So we may not even have a register called DAT. We don't. So our new model is that we can freely read and write the disk, track, and sector registers to specify where the I/O is going. The status register tells us whether we're ready to accept data or whether the data is available or not. And the control register will say whether we're doing a read or a write. If we are doing a read, then well, let's implement and then test on this one. So what I want my model to be, control byte values, we're going to start off with those. So NOP is do nothing. So write control, we're going to say byte CTRL. Oh, almost forgot. We need to have bdev all. No, we don't need bdev all. Wouldn't hurt. Okay, so I've removed the bits of the test that aren't working yet. So what I envision here is that we will check the status for idle. I'll put the status first because that's what we are going to be doing first. We're going to read status, we're waiting for it to be idle. And then we're going to say, write the disk, write the track, write the sector. So we're going to set up the disk, track, and sector numbers. And then we're going to say read. And we're going to wait for the status to come back and say, go read. So that tells us that we have a data byte available. When go read is there in the status byte, we have data. Actually, RDY for read ready, and RD end. Once we have read the entire sector, RD end will come high to say that we're done. And then I think what I'm going to do is we will stay in RD end in the status byte until somebody writes a NOP again to put us back to idle. No, when we're done reading, we can go back to idle. So we'll be busy until we are ready to read. So for the write, somebody does everything and they put the writing. We'll go busy until we have set things up to accept data. Then we'll say write ready when we're ready to receive each byte of data. And go busy between them if we need to wait for some reason. And then we'll go back to idle when we have written the entire sector. NOP, we are not going to require anybody ever writes NOP. So here's the thing. Let's document this. To read a sector, wait for status equals bdev stat idle. Update. write disk number 1.26 to DSK. Actually, let's go 0.25 to DSK. Actually, disk number. Okay, then we say write bdev control read to ctrl. There, you know what I mean. For each byte. Okay, so we're going to alternate between busy and read ready. So what I'm going to do here is, if caller wants to end early, send dev control nop. So sending a nop command will serve as a reset to the controller. In fact, I think I will set up the logic in the implementation. So if somebody is in the middle of reading and they say, write, boom, write, what it's going to do is it's going to say, well, you must have set these up. So if somebody starts mucking with these guys, I think this latches DSK. Controller ignores DSK, TRK, sec values. So on a real system, the moment we start to read, at some point we're going to have to take some time to drop the heads on the disk and seek to the proper track and wait for the sector to come around. No, I think I'm going to force this behavior. So you send a nop to say we're end. So to end the transfer, So first of all, if it's busy, we have to loop until it's not busy. Then we have the option of ending the transfer, which is CTRL is NOP. And to break out. Make this more explicit. Wait for stat not equal to. Is there any weakness there that could cause real problems? Well, we have the problem. We have two ways of exiting. I'm going to eliminate that. So we are going to wait for stat equal to RD, receive byte data. We do need to be able to terminate the loop. Oh gosh, we do need to be able to terminate the loop. See, if I don't think this through in terms of what I want the code that talks to the controller to do, I won't be able to implement properly because I will implement to the wrong model. So if we get anything other than read ready, busy, or idle, then we have an error. So that's what our assembly code for reading a sector looks like. Allow breakpoint. Report error to console. Writing a sector looks exactly the same, except this is get read source of write transfer write to dat register. So the difference is only in what we're doing here or here. Okay. So with that set up like that, I am going to refill my coffee mug and we can start implementing. So what I'm going to have to assume here is that we have a bit of storage that the simulation is going to fill in for a given disk. Because we need to be able to provide data to and from the disk image. So storage for the mass storage state machine. What I want to do is provide state for each disk. Now, I could continue to use this dodge of having an implementation that does the right thing. I think what I will do is have an impl function that returns a pointer to the data for disk track sector. And that will be called when we do the command. So here, when I issue the read or the write command, that will then disk controller locates bdev impl locates the data storage for disk content. So this is going to be a function that returns a pointer to a void, and the parameters it's going to take are the bdev. So byte star I'll call this seek. And seek is going to be handed a struct bdev star. Like that. And it won't know whether it's a read or a write yet. Yes, it will, because I can leave that breadcrumb. Oh, nope, let's just do ImpleSeek. I'm going to do this really simply. Eventually, this should turn into either memory mapping a file or reading a file into local storage and then writing it back in the end. I like the idea of memory mapping. So ImpleSeek gives us back a byte pointer, which we can either read or write. And we have a data cursor in the end. So type def bdev seek fn byte. Is that it? Yeah. Oh, that's right. Yeah, we have to use void star because we can't say struct sbdev because, well, we could say struct dev. So there was a reason why I didn't split that up. I think it is because indent does things badly. That doesn't look too bad, but this doesn't line up properly. So let's just use void star here. Okay, expected close paren before C-stir. Really? Right. So the seek function really wants a context at the end as well. We'll provide the bdev first. No, let's just provide the context. So it'll be up to the person registering the function what the context looks like. There. So now we're not explicitly passing the bdev in. That'll be the job of the context that we send into the seek function, which may include a lot more. Seek may, in fact, own storage for the disk. So now we need to go through here and fix things up. So initialization, we set name, we initialize pdata. Okay, so initialize all of that. Grab all the stuff. We're not going to grab seek and cursor and bdev all. Right. Or should we? Yeah, let's grab cdef cursor. This needs to look like byte star cursor equals bdev arrow cursor. And seek, same thing. Is my indenter going to keep up with me? It is. Let's put all these in column 72 because I am tired of re-indenting.
This is she.
Quietly just continuing to move onward. seek underscore. Microphone needs to not be between me and my keyboard. Seek context and cursor. So we set the seek function. I'm going to also force cursor back to null. So if somebody changes the seek function, we don't have a leftover cursor. So one issue here is if I write this the way I think I'm going to write it, the simulated system could continually write bytes, boop, 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 right to where the cursor is. And I'm thinking that we need to arrange our code so that, in fact, we go idle at the end of a sector. So not just cursor. So when we call seek will have to update cursor and limit. So let's set up a cursor limit as well. So in our code, when we write, if cursor gets to cursor limit, we're going to say we're all done. And the seek function doesn't return a byte anymore. The seek function returns a void. Cursor, don't have a cursor lim yet. So we'll call the seek function with ctx. It needs to fill in cursor and cursor lim. We will then read and write bytes at cursor auto post increment. And when it post increments to equal lim, we'll null these out so we don't write beyond that. And with these nulled out, it's going to be back to idle. Now here, I don't think we have a difference between read and write ready. So if we eliminate the difference, then it's up to the caller to know whether they're reading or writing. And the disk controller doesn't care. Well, if you send me a byte, I'm going to write it. And if you read a byte, we're going to give it to you. So super de-duper simple. So this is stat data. So for now, I'm still leaving this check versus data. If these are the only three values that the status register can take on, then we should never be able to take this error branch. We're going to keep it, though, in case we do. And now our status is going to be either idle or busy or data. And I think for a first implementation, we're never going to be busy. Just a thought. Because we might be infinitely fast. Actually, let's eliminate the busy state completely. So the status byte really just idle or data. We don't have to wait for stat equal to idle. We can just update track sector and disk and then set write. I'm not going to have a NOP. So we update these, we say write, and this locates the storage. And we're basically going to say there. So basically we're going to write all the data we think we should write. And if we ever get back a stat that isn't data, then we've got an error. And we don't wait for NOP here. So read a sector is just write a sector in different pants. I'm going to write that in C notation. So we're just going to say start HL ++ equals dat. Boom. This is a write, so this is dat equals star HL ++. We're modeling an infinitely fast controller, aren't we? The reason why I want to make these routines as small as possible is because I do need to be able to write a boot sector, so a 128-byte program that reads in the first two tracks. And I want to be able to conceptually load in a program that can read in the boot sector. So the default value for track sector, disk track sector, needs to be set up in the controller so that if we just issue the read, so let's say we're sitting at a front panel, if we just put in the code for read disk and send it to the port, it should do the right thing. Now, the problem is we're not doing DMA here, so no, I won't be able to do a bootloader like that. Darn it. Okay, so I need a boot program. I can't just have something you put in with the front panel. I remember several computers of the age, there was a specific thing you put in on the front panel, an address. Sometimes it was an address, you'd say go at that address, it would run a boot param. Sometimes it was literally, you would toggle in several instructions to do the bootload. We'll use a boot ROM on this one. But this means, how about we do a bdev control reset. So a 0, 0 to reset the controller. CTRL equals bdev CTRL reset. Selects first disk, selects first track, selects first sector, so the only difference between read and write is whether you are reading data or writing data in this word. And in fact, RD and WR can be the same implementation because we don't care whether you're going to read or write. So this is really control seek. So we continually are simplifying what's going on. The only difference there is which way this is going, whether we are reading from the IO port and writing to HL, or reading from HL and writing to the IO port. But this code is getting shorter and shorter and shorter because we're basically saying that this controller runs infinitely fast. Now in hardware, if I wanted to actually implement this in discrete logic, what I would do is I would simply put the CPU in a wait state. And that would mean that to simulate that kind of hardware with a wait state, we would then need to simulate this, where we're writing to memory. We'd have to do a wait state during IO read and IO write operations. So if we were not infinitely fast, we'd have something here that says in the software wait for data ready. For data. So, but we're not going to do that. We're going to pretend that we have a controller that can accept data as fast as the CPU can send it, and it will go off and do other things. And I'm not putting any sort of termination condition in. I'm just saying once you've done it, it's done. You do the seek, you read the data, you're done. You do the seek, you write the data, you're done. Boom. Super duper simple. Now, status is idle or data. Well, we don't have status anymore. Literally, we don't have status anymore. And literally, we don't need to have the control register anymore. Watch this. Boom. So what we're going to do beyond the hood is when we get the read and write to the data register, if cursor is null, then we're going to go pick up the information here, and we're going to set the cursor and cursor limit by calling seek. And we're going to then transfer data, bada-boom, bada-boom, bada-boom. And when we reach the end of a sector, we have two things we could do. We can null out cursor and cursor limit, or we can leave them there and implicitly seek to the next sector. I like the idea of implicitly seeking to the next sector because it means that if I keep doing sequential reads, we can read sector, 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 sector. Get to the end of a sector, we can get to next sector. We get to the end of a track, we can go first sector, the next track. So literally reading many sectors is just continually moving more bytes. If you read beyond the end after each, read after reading. Reading data after the last byte of a sector will get you the first byte of the next sector on the track. Reading data after the last byte on the last track will get you TBD. Okay, so we have now simplified things like crazy. And what I'm going to do is I am going to let the seek function handle all this. So we'll call seek, and it will get us back this null. And the idea is when we reach that, we will get null. The seek will need to increment disk track and sector internally. So I'm thinking that when we call seek, it will compute the location of data for disk track sector and set that up, and then it will bump the values in disk track sector to point to the next one. That's all behind the hood. But there is what our PIO-based disk controller is going to end up looking like. And I'm glad I spent the time to refine this down to practically nothing. Disk track sector, data read, data write, data, and our seek function, and the cursor information that we need to make it work. So let's go look this stuff. So we read. We no longer have a status or control register to read. Seek. Seek context. Cursor, cursor, lim. bdev all. We initialize things. We no longer have a stat read or write. bdev set seek sets this stuff up, initializes cursor. Invariants, disk track sector, data read and write. We no longer have these guys. Let's have a there we go. So invariant, for the invariant to pass, we have to have a seek function. Now linked is going to say we've got it. Once we've linked, we're going to grab all of the contents and we're going to hook up all of this stuff. We have 3 registers, and we have a read and a write of the data register. We have no status register, we have no control register, we just have move the data. Okay, so now if we try to run this, it's going to come up with a failure. Of course, we haven't implemented anything yet either. Do I have stub set up inks? I believe I have stub. Yes, I do. No, let's go ahead and implement. I can write this now. With this information in hand, when they write to the data register, I'm going to say if cursor is equal to null, then we're going to say seek of seek context. Okay, so if cursor was null, then we're going to do this. So if cursor is null, or cursor equals cursor lim. So first of all, cursor is null. Then we're going to do that. And we need to refetch cursor. Now, actually, null equals null, so I could just say if cursor equals cursor lim, then do the seek. Now we are writing, so this says star cursor plus plus is equal to data value. So if they're now equal, we now set cursor equals null, cursor lim equals null. So we're not going to call seek again until somebody tries to write or read data. Else bdev arrow cursor equals cursor. So there's write. Read is the same thing, but it's data arrow value is equal to star cursor plus plus. So we now have the ability to read and write data, which will interact with the seek function to locate where we're reading and writing to and from. No seek function. Oh, no. But I believe that's implemented everything that we need in bdev.c. So this guy in bdev.test.c. Now, this guy is actually responsible for doing real work. So type def struct bdev seek ctx. How about we give that a good name? S bdev ctx. Okay, so we have a bdev, and what else do we need to know? This is going to have access to the file. So byte star data and a size of the file. Files can get fairly large. I am going to have size t data len. Now, data may be dynamically allocated. It might be something we get from mmap. It might be a static array. If we have a scratch disk, we may have a scratch disk we implement where we just bop in some data. I think for testing, what I'm going to do is so for testing, we're just going to do a scratch data. So if the SA800 ignoring all of this, we're looking for the capacity. Access time track to track is 8 milliseconds. So we have all of this information about timing. So we could simulate head load time, settling time, track to track time. The average is garbage because that depends on how many tracks you're seeking. Rotational time, recording density, yada, 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 all the way down. Where does it have number of tracks? So IBM format is 26.6 kilobits per track. That could tell us a lot if we didn't find anything else. Just making sure BPS 128. SPT 26. Track per disk is, I think it was 35. We'll find out. So a byte per disk is TPD times SPT times BPS. Going back to looking for the number of tracks supported on these guys. And we're going to do down to find disks per controller is 4. Actually, let's just do disk per controller and tracks per disk, sectors per track, BPS. Let's let our, there. And now we don't need to do math. We'll just let the subscripting magic do the math. Since this is an array of arrays, we're not doing pointer and direction. We're just doing pointer math, which is really very nice. Track 0 indicates we're at track 0. Sector SA801 has hard sectoring. I used an SA800, which is all soft sectors. Just change on it. I thought this had the number of physical drive specs. I wonder if they just kind of assumed that the number of tracks available was a kind of a host system thing. So somehow I thought I remembered seeing in here the number of tracks. One of the reasons I saved this file. Well, we may have to do math. if it's 2 megabits per disk and 26.6 kilobits per track, this is divide 2.0 by 26.6 So this is 77 tracks. Roughly. And interesting, 2048. Right, okay, that comes out. Okay, so it's rounding it. So 77 tracks total, tracks 0 through 76. And sectors, so 26.6 kilobits in IBM format. Yeah, 128 bits per sector is 212. Whoa, wait a minute. Oh, it's kilobits. .6. This is 26 sectors. So 26-ish sectors and 77 tracks. There's a little bit of slop in there because there's space in between. Now my actual capacity is going to be 8 bits per byte, 128 bytes per sector, and 26 sectors, 26,624, and this rounds to 26.6. Okay. So double density, IBM format doesn't have a double density, but this doubles everything. I believe it doubles the number of sectors. Capacity number is selected to match IBM format 8-inch disk. Insert. Times 128 times 77 tracks times 26 sectors. So a historical note, there's long been this tension between powers of 2 kilobits, megabits, and so on, and decimal kilobits, megabits, and so on. When you're scoping out computer memory, it's innately power of 2 because you're using binary to present the address. So if you say 64 kilobytes of memory, it's going to be 65,536. If you say a megabit of memory, megabyte of memory, either way. It's going to be power of 2. But magnetic media gets quoted in millions of bits. So when we look at an IBM diskette, it stores 2,050,048 bits. If you expected to store 2 megabits of data, binary, then you would overflow the disk. And if you were expecting a megabit, you would get something slightly short of that, and you might get upset. This begins to raise its ugly head when you get up to a gigabyte, because the difference between a binary gigabyte and a decimal gigabyte is pretty big, and people can get really, really teed off about the amount of disk space that they are short if they don't understand what's going on. Anyway, as long as you understand what you're getting, then you can deal with it. Just expect that when somebody quotes to you the size of a piece of storage, if it's not actually RAM sticks, it's probably going to be a decimal, which is why people started using KIB and MIB for the binaries to be explicit. So if you say my network data rate is 3 megabits, it may very well be 3 million. But if you say it's 3 MIB, then you know you're getting the binary, which is slightly larger, like 2.4% per kilobyte. And if you're talking megabits, it's 2.4 squared. Anyway, it diverges kind of slowly, exponentially. So we've got that. We have our disk here. We have our storage here. I need to do a bdev ctx init. Okay, I am going to pre-format my scratch disks to have this 5-5 pattern. Actually, I could do even worse. I could do a barber pole through there. Yeah, no, let's preload it with zeros. Still moving onward. So here's our context for the disk controller. Now down here, when I initialize BCTX, I'm going to also set up the callback here. So we're going to go bdev setseek uppercase. Bdev ctx seek is my function. This is where all the hard work happens. So not just a stub, I'm going to just fail that outright. So with our much simplified accessing here, we still need the macros for doing that. We're going to do the same thing with writing the registers, reading them back. So bctx init there we go. bctx arrow bdev is the wrong type. We don't own it, so we need a P right there. DPC and TPD, SPT, BPS. Actually, P. Now, for the testing, we always know that's going to be true. We're going to assert it anyway. I was going to remove it, but I decided not to. Bdev, all of bdev. So now we have all the function, all of the fields from bdev. There. So I believe that actually ran this guy. Did we get into it? Yes, we did. I'm going to leave those in while I trigger this together. We write a few values, get to the first sector, track sector, yada. To do exercise, read several sectors. there's our test plan. So one thing I want to do here is assure that we can have some kind of data that makes sense. So I'm going to say C plus T plus S plus B. So we get something here where if we're in the wrong control, D, this is D, not C. If we're in the wrong disk or controller or track or sector, format the blank scratch disks to have data we can use to detect access to the wrong area. Now my intent is that I should be able to have a disk controller in a real system which can access a disk file or create a disk like this and bring in a Intel hex format file to load up contents of the disk from the hex format file if we want to do that. Load in a binary data starting at an arbitrary track sector number. Remember, this is all contiguous, so the sectors are laid out in ascending memory order and the tracks are laid out in ascending order and so on. So we can just write to this stuff as long as we check bounds. So first of all, read several sectors. What I'm going to do is I'm going to read let's just read the whole frippin' thing. So we do that. We're going to say WRR TRK DSK D. So the other trick that I'm going to do, track starts at 1. So there's our definition. So we need to take that into account. I am going to consistently use sector from 1 less than or equal to SPT, which means I'm going to consistently say S minus 1 here. I'm going to use the sector number like that. It's too bad they decided to have 1 be the first sector. It could very well be that the sector number needs to be non-zero for some technical reason. I don't recall what that might have been. It might have had something to do with the synchronization. So what I'm going to do here is I'm going to set sector to 1 here, and we're going to read, and I'm going to let this auto forward to the next sector of each track. See, I want to do 2 things. I want to check auto forwarding across each one, and I also want to check explicit. Let's do this twice. In fact, let's do it in forward order. Read the whole disk without well, this is real simple. This is RDR of DAT. RDR just piles it into what? RDR puts it in B. Oh! Let's put it in something called data in lowercase. Same thing, but now we're going to do it in reverse order. Same thing, but reverse order and explicit. So 4 int d equals dpc plus 1 minus 1. D is greater than or equal to 0 minus d. So we're still going to get the bytes in order. btx seek unimp. Got it. Okay. Let's set byte expected up above. That's some bullshit. Assert EQ integer is being passed exp right there. What's going on? Expected, call into op integer of expected here. Oh, we have an exp right there. Bingo. Okay, so lesson learned. These need to be set up so that they don't hose us. So this is a bit of thing that I should have remembered was using these dunders before the name inside macros and only inside macros so that we don't have local variables inside macros stepping on variables in the calling context. That's better. So now we can declare exp again at the top. So read all storage without updating. Same thing, but reverse order, setting them each time. Then we need to settle on a few sectors to write to, and then read them back and verify that we got the right thing. Let's get this part working first. So we're getting down to here. So ctext seek, that basically means that we need to set cursor based on disk, track, and sectors. So we are going to say BCT, let's see. We already have cursor, we just need to change it. Okay. Explicitly write back our results. And there's our seek function. Oh, haha. Sector -1 because sector 1 is the first sector. Okay. So we're going to do this just in case we change the implementation so that this value, instead of being an array of an array of array, it's an array of, at some point, pointers. So in case what we're getting here is a pointer to allocated memory for one sector, we don't want to set our limit to the beginning of the storage for whatever the next sector is, which might not be contiguous. So here we are contiguous. Now let's keep with our idea of update the variable and then store it explicitly. Oh, the other thing is when we're done, we need to increment our cursor. So if sec is less than spt, so if that's not true, then sec arrow value is back to the first sector, and we bump track. Okay, if track would increment to TPD, then we write 0, and we need to increment what? We do not fall over onto the next disk automatically. I don't want that to happen. Which means here, what I want to do is just always write back the track value. And we do some out of range checks. So if disk is greater than disk per controller, so if we are out of range, then we keep a null in the pointer. Okay, because we know that cursor and cursor lim are null when we're calling context seek. So we look at these and we say, ooh, let's check. Let's check each one as it comes up. Then we increment. We increment sector. And if we rebound, then we increment track. And we're going to head and bump track off the end. So if we bump off the end, we are going to end up with not looking at anything. That's correct. So we get in here and we're computing A01 is at offset 0. That's correct. Okay. So the other thing is, I believe that I forgot to write back the updated cursor. No, I didn't. I did write back the updated cursor here. No, we don't need to print that we're triggering seek because we're, oh, let's see. Triggering seek. Okay, by using data 2, when I set these guys, that allows me to properly run the callbacks for people that are watching the contents of those registers. I kind of like that method that I'm using for printing out the address information. Let's do that inside our testing so we can see what we're doing. So disk track sector, print that we're reading it. So we get to our second sector, our condition is failing. So when we got to here, this should have triggered bdev to clip the cursor back. Yes, it did. But I did not actually do that. Now, we don't need to do that because we do check for equality, so we're just going to do that. There. Now, I think what would have happened there would be that we would have continually reread the last byte. There we go. So it starts and ends at offset 0. Those look right. So we can remove these stubs. Got to comment them out because they may be very useful later. And advanced cursor to equal lim. Again, we don't need that anymore. So we're getting into the reads here. And we have a test condition failure here. Disk track sector offset. Disk track sector byte. Damn it. So we head forward through the drive. A, B. Track 0 through 76. D0426 starts at somewhere. That's not the one we were supposed to be reading, which means I'm setting the wrong register. Disk track says TRK. Then we attempt to seek to 76. 25. We are overreading somewhere. disk track sector. Disk 70, disk D76250. And seek is saying which condition are we failing? There we go. This is saying the track is greater than or equal to TPD. Well, it's need to be, yeah, greater than or equal to. So TRK has a bad value when we're getting to seek here. Probably because TRK got incremented here. It did indeed. So we read the last sector and it incremented the sector, which incremented the track, and we didn't rewrite the track. So I need to always update TRK here because this may have note, always rewrite TRK. It may have been incremented if we just read the last sector. So the other way to do this would be to modify the auto increment stuff. So this means that a lot of the stuff that's in CTX-seq in the test is going to be required in real implementations as well. The difference will be the limits. So instead of writing back the thingy, what I will do is I will store off the previous, how can I do this? I would need to differentiate between somebody continuing to read off the end of a sector versus somebody selecting the same sector again and saying read it again. And because I am just allowing reads and writes to the track and sector, I don't think I can notice that somebody has written or not. So yeah, okay, I'm just going to require that we always rewrite the track when we rewrite the sector. Let's put that in bdev.h. That's actually a better. That's a better way of saying this. Okay, so there we have it. So now we need to get back to bdev test.c, and I need to test some random sectors. So we'll look at two different disks. We're just going to mess with our increments and decrements. So track, I'm going to do, track is, say, 13, track greater than equal to 0, track minus equal 10. And we're going to read sector 14, PT, sec plus equals 210. And we're going to duplicate that. And what we're going to do is we're going to write data register. And this is going to be something different. Well, I'm going to invert the bits of it. Oops, here. Don't mess with that, right? Several. Let's just do that. Now what I'm going to do is assert EQ integer, and we're going to go into BCTX of disk track sec minus 1 B to look for that data. So I'm not testing to see if any other data was modified. We're going to read it back. And again, I'm not testing to see if any other data was modified. So this is not a strong test. Here we go. And that worked. So we wrote our modified data to the scratch disks, and we got it back. Okay, there's our test. Yeah, that should work. So now, for the systems that we build, we will need to provide a similar BCTX that provides access to data on any one of n disks, and we'll need to work out how to find that data and update that data, probably by M mapping files. It will need to provide a seat which does essentially this job. I'm thinking we might move the auto increment into BDev, but that would require the auto increment to know how many sectors per track existed. And that may depend on the loaded media. For instance, one disk you plug in may be formatted with 26 sectors on each track, and another one you plug in might be formatted with 16. So you never know. How we determine that is going to be dependent upon the simulation providing the specific controller. So we are not going to put that in BDEV. We literally would have to ask the implementation, BDEV would have to ask the context, hey, how many sectors are there? It's just easier for this guy to do the right thing. And we have a code reviewer. Hold on. Hey, meow. So let's go look at our code again from the top. Move my microphone out of the way of the cat so she can curl up and look at what's going on the screen. She does not want to look at the screen. She wants to be rubbed. So she's saying, explain it to me. So our disk controller, on the right, we see what it presents to the system. It has 8-bit registers for which disk, which track, and which sector are going to be accessed the next time we start something. And I already see a weakness in that we're only going to select the disk, track, and sector when we run out of the current read. So we need to have something that will tell us either reset the controller or tell us that we are reset. And I think what we need is a reset the controller thingy. So we do have a reset signal coming in. Now this isn't system reset. This is going to be hooked up to an I/O port. So you'll do an out instruction somewhere which will do a reset. Okay, so that's the state we should get. Okay, so Lucy, we already have a bug report from our code review. Once we get out of reset, we have a disk, track, and sector register each. Disk has a range from 0 to the number of disks that the specific controller will implement. BDEV won't know about that. That'll be down in the implementation. We have read and write edges for disk, read and write edges for track and sector. Track is 0 to the number of tracks on the disk. Again, we don't know the number of possible tracks. We know that we are going to support up to 256 tracks. And it is up to the controller to detect that it's trying to access a track that doesn't exist on the device. Sector numbers. By convention, sector 1 is the first sector. So we have a sector 1 through N. So we could support up to 255 sectors per track. This is actually a bit weak. If we'd started at sector 0, Well, the upside of that is we would have 256 sectors. The downside is all of the sector numbers that anybody talks about in any documentation ever for decades. Sector 0 doesn't exist. Sector 1 is where you start. Bugger. So we're going to maintain this. So sector 1 is our first sector. Number of sectors per track is up to the controller. And in some extreme circumstances, different tracks on a disk may have different numbers of sectors. So for instance, a rotating media, there is physically more media on outer tracks. So in theory, you can place more bits and thus more sectors on outer tracks. And the way you do this in practice is you spin the disk at different speeds. So for inner tracks, you spin the disk faster. Angular rate is faster. And for outer tracks, angular rate would be lower, giving you the same bit density on the disk. Now that would be changing the speed of the disk every time you seeked, which involves spinning the disk up and down, which is expensive. So you tend to have some compromises there. The Apple Macintosh had a special disk that had two heads. And as you seeked back and forth, one head would be on one side of the axis of the disk and one would be on the other. So you might be, the left head would be accessing track 0, while the right head might be accessing track 35. And you would go back and forth by changing which head was in contact with the disk. You'd also have to spin the disk up and down. This is, I think, called the grasshopper disk. And the sounds were kind of neat because you could hear it spinning up and down, dee, 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 up and down. And as you seek toward the middle, okay, both heads would come toward the middle, the difference between the sounds would change. So you could actually listen to this disk and you'd know what's happening. But it involves spinning the disk up and down a lot, which takes time. One example of how this was later used, I believe that CD-ROMs are written in a spiral, and the idea is that you spin the CD-ROM up and down to maintain a constant linear velocity along the spiral groove. This cat is so incredibly happy. I need to, at some point, have the camera set up so I can show her. She just curled up on my chest, purring away. I think she's saying that the change that does the reset is all we needed. Anyway, so that's disk, track, and sector. The idea is that we would write those in a real physical system. We would then have to wait for the disks to spin up, the heads to land and stabilize, the seek to happen so we're on the right track. We'd have to wait for the data to get under the head, and then we could start reading or writing data. With this system, I'm assuming we're magical. That's all going to happen in hardware on the back end. Maybe the disk controller is this huge card that's as big as the computer, which was not an uncommon thing. And what we're doing here is we're going to ignore the fact that it takes time before we can read the data. We're just going to read it, boom, we're done. We're just going to write it, boom, we're done. We have no status word. We have nothing we can do that says, okay, you're go to read or you go to write. We will add those when we need to. At some point, what I want to simulate here is an actual disk controller card you might see in the wild, but those do use DMA and interrupts, neither of which we've implemented in the simulation so far. So for now, we're just going to read and write the data. And the first time you read or write a byte to a sector, we will do all the math and figure out where to put the data and get the data and put the data appropriately. And when you run off the end of the sector, we will recognize that. So the next time you read or write a byte, it's the next sector. And if it's the last sector, if you just finish the last sector, we'll go on to the next track. The way that's implemented is when you do the math to find the data for the disk from the first sector. At that point, we will bump sector, and if we bumped it past the end, we'll rewind sec to the beginning of the first sector and go to the next track. Now, if we are selecting a disk, track, and sector that don't exist, then we'll leave cursor and cursor limb both set to null, or maybe both set to each other. In any case, we'll leave them set to values so that we know in bdev.c that we don't want to actually move data back and forth. So we go to here. When we set the seek function, we're going to reset cursor to force us to call the new seek function when we do our next byte. We have an invariant that we can check, which checks our invariance of all of our edges and registers, and then checks to assure that we have a seek function. When we are linked, which means people have hooked up everything that needs to be hooked up that we need to import, we're going to check invariance and then establish our services for all these edges. So we need to add a edge on fall of reset that puts us back on a reset condition. And I would type that, but I've got one hand with a cat and one hand with a mouse. We have three simple registers, reading and writing. We have all the work done in read dat and write dat. So read dat says if the cursor is at its limit, which is also true if they're both null, then we call the seek function, re-update those. If we're still at the limit, then we're nowhere. Which means if we continually read and write stuff off the end of a disk, we will be falling through this seek function every time. So for media change events on real controllers, the controller itself would want to hit the reset so that the bdev is in its reset state. If it's the active disk that got changed, or maybe not. But yeah, when new media occurs, seek will have to compute the new location for reading and writing from the new media. And I've got a problem. The cat has her head locked onto my other hand, so she's got both hands. I can't even move the mouse. Right, is similar. Again, same logic. The only difference between read and write is whether we are moving data from the data bus to the cursor or from the cursor to the data bus. Bump the cursor, it will eventually equal the limit, and we're done with the sector. So we need to write the reset function and test it. I think we can test that by doing our random read test again, but hitting reset halfway through the sector and then skipping the rest of the thing and making sure that we're picking up with the next sector properly. Should reset change disk, track, and sector? I think it should, which means that when we do that reset, we're done. If we want to try several sectors, it means we need to reselect the disk in the loop that is going to pick up the next sector. That's fine. Okay, so I am going to try to put this cat under a tent somewhere because she is going to sleep with her chin firmly latched on my hand. Sneak my hand out. There you go, kitty. Let's go find a tent, Lucy. I will be right back. Okay, so now we need to do the controller reset that Lucian showed me I needed. We have a reset signal that we need. I'm going to say bdev reset to make sure that we know it's not just a system reset thing. There needs to be an actual reset signal just for the bdev. bdev init. We need to do a edge init of bdev reset. No, let's just call it reset. And we need to have a edge here, like that, so that everybody's going to have reset available. We do an edge init of reset. We are going to do a edge invar of reset. We're going to do an edge on fall of reset. Yeah, I had caps lock on, but let's go ahead and just use that. Well, no, there's our name. Okay, so once we've done that, I actually do not need, well, this will make it handy. So what are we doing for reset? We are saying dsk arrow, let's see, data to dsk 0, track 0, sec is 1. Then we're saying bdev arrow cursor equals null, and cursor lim equals null. So reset will reset the state. It doesn't reset seek or seek context. They will get called again with us on that. So if we do a reset and then start reading immediately, we will be reading the boot track. Kind of convenient. So bdev reset undefined because we never did the declaration. Actually, I want to put this up at the top of the static functions as well. So before all these impls, we're going to get him. And up at the top here, we're going to get boom. Now bdev test. We are going to have this reset thing. So at the end of this facility, I'm going to pull a reset line. Actually, let's get a to do. That's no longer to do. And read the sectors we wrote. Somewhere in the middle, we're going to do that. Then we're going to bonk an edge. That's just going to be edge low and edge high of reset. And that's just like reading or writing an I/O port. We'll figure out what I/O port to connect that to. When we start connecting to I/O ports. But we'll be on an I/O port. And now we want to go back to here and see what we get if we just start reading. We're going to read the whole boot sector from the scratch disk. So this would be 21, and we're reading 32. Okay, so yeah, there we go. Warning, macro expands to multiple statements. What? I haven't seen that before in context of here. Oh, right. That's a great warning. Oh, nice. That saved me from a whole bunch of pain. That literally would have incremented tau that many times and then read once. Okay, this is another reason why C programmers learned very early on to always use braces even for single statements, because sometimes a single statement isn't. There we go. Now this is coming up with a cert not busy on some edge somewhere. And it's probably in our reset function. which we just put in. So this says someone is doing a pull on the edge for reset. And we're going to say invar. Can't do that because edge invariants fail if the edge is busy. So we can't check the invariant of an edge from within something triggered by that. So we cannot do the invar. Now, I could relax that in edge and allow people to call the edge invariant even though the edge is busy and have it check everything but that. And that might not be a bad idea. Let's do that. Now, there's someplace else that we did this as well. I've run into this a couple of times now. It might have been in other work inside BDev. Let's take a look. Take a quick look at the invariants. Adder invar. So BDev invar checks everything. So it's things like where we're calling invar from places where we might not be invariant. So BDev write dat. Would be a problem if BDev invar checked that signal was going to dat. And that's, yeah. So read and write for block devices is not actually a performance critical thing. So BDev invar. Read dat, write dat. Bring invar. Cdev invar. Yeah, here's where it was. So now Cdev invar can check the edges here. And it can also make sure its invariants are met here, all without causing problems. Clock, data invar, some of these guys are checking it on the way in and the way out. That's older paranoia, but for those fundamental things, it's useful. Decoder invar calls up the edge. Decoder is timing critical, edge is timing critical. So I'm going to scan the list here, see if there's anything else that jumps out at me as being something I want to check. I think the rest of these are good. So what have we tested? We've tested reading the whole disk. We've tested reading randomly. We've tested writing some sectors and reading them back and verifying they're good. We've checked reset in the middle of stuff, followed immediately by reading the boot sector, and that works. So I think we're good, except of course we need more comments. To do, add comments right there. In pdev.c, we need a to-do, add comments, which I can do off screen. And these commented out lines, I can get rid of them because we know they're working. I think that's it. So kind of a long session this time, but we now have block devices working and a test that mounts up some scratch disks. So with block devices and character devices going, and a working CPU, and a working memory, and a working ROM, our next step will be to start building a system out of it. Now, I was going to take my channel name Voidstar Farsight. I was going to make a Voidstar 8080. And then I realized that there is somebody out there with voidstar.com. And what the heck? Okay, Voidstar is a pointer to nothing, widening the bell curve since 1975. Got some. It looks like a hub site. Yeah, okay, so this is just a guy that has a whole bunch of random links to stuff around the network and has been doing it for a long time. I am not sure whether he's actually been doing it since 1975, but he is certainly welcome to use that. I don't pretend to own Voidstar, but he's got the stuff. So the website shows a copy left date of 2001, so he has been doing this for a long time. It's a fairly old site and got dead links to Twitter, dead links to InfoHazard, PayPal, Look What You Made Me blog. This may be a dead site, I don't know. I have no idea if this is current. Might be cool if I could acquire this, but there may be a whole bunch of people using it, so maybe not. I may have to contact him. Anyway, so given that, it probably would be okay for me to call this the Voidstar 8080 because he's not really into old computers. He's got a whole bunch of neat links there. Actually, I kind of like his website. Yeah, I'm not even going to think about wanting the domain now, because this is actually kind of cool. I'm pretty sure that if I call something a Voidstar 8080, it's not going to be confused with voidstar.com, so that's good. And we can start writing our boot code. So, thinking about the system we're building, we're going to run two things that are important. First of all, I want to be able to run CPM. And second of all, I want to be able to run FigForth. I already have the listings for FigForth 8080 I have an assembly file that assembles to this. This is actually an automatically generated listing from the ASM code that I have on hand. This version of Fig4th assumes that it's running inside CPM, which is good. Long term, and the reason why I'm using 16 kilobytes of ROM instead of 2 is I want to do a fairly deluxe fourth in ROM. And 16K will get you a heck of a lot of fourth. Okay? The idea there is that we have a system where we can work with fourth and ROM, do a whole bunch of things, then I can go back and modify the boot ROMs, the fourth ROMs, to have even more stuff. So we got a lot of space to do stuff. Fourth is a fairly compact language. The equivalent of a subroutine call is 2 bytes versus the 3 bytes for a 8080. So there's, for those of you who don't know fourth, think of it this way. I want to do a thing, and to do a thing, we break it down into smaller things we want to do. So I have my foo, step 1, step 2, step 3. So foo might be a subroutine that just says call step 1, call step 2, call step 3, return. So that's what fourth is. But then you start looking at details. So instead of a foo being a bunch of assembly code that's calls, it's now just going to be the address of step 1, the address of step 2, and then the address of step 3, and then the address of something that says return. And those addresses might point at actual code. So now to run it, we would have an interpreter that has a pointer at the beginning of this list that says, fetch the word and go call that function, then fetch the next word and go call that function, then fetch the next word and go call that function. I'm not sure if we... Well, fourth goes one step further. This thing, this step 1, doesn't point at code. It points at a word of memory. It actually points here at the code field. So we have a list of addresses here. Each one points at a thing which has a pointer to the code to execute followed by parameters. So step 1 might be do something, which might be push a value onto the stack. And step 2, fourth is a stack-oriented language, step 2 might be increment the thing on the top of the stack. And step 3 might be print the stack out somewhere. Okay? Or step 1 might be, oh, I am myself a list of things to do. So step 1's code might be push the instruction pointer and set it up. So this is fourth in a nutshell. This dictionary format, each one of these subroutines, we have a optional name field, so we can store the name of the function in memory just before it's in its implementation. We have a link field, which points to the next older word, so we can define new words in the fourth dictionary by writing their name, writing a link to the previous end of dictionary, and then we write a code field that says when this word is executed, here's the machine code, pointing at the machine code to execute for this word, and then we have parameters. And the most common word is a subroutine that calls things. So its code field would say, do a subroutine call, and then there's a corresponding one that says return from subroutine. And the implementation of it is here. So next, when you reach the end of a subroutine that calls subroutines, what you do is you call this, which says, when you reach the end of a, how do I put this? You're running some code for a word. At the end of that, you want to step to the next word in the subroutine that calls subroutines, that called you. So we load from IP, 2 bytes. IP is it's actually the BC register pair, points at this list that we're interpreting. and we LDAX that and move it into L. We LDAX again and move it into H. This is a little awkward on the 8080 because we do not have read from memory and increment pointer. LSI 11s were really nice because you could say fetch byte at this address into there and increment. In fact, I think you could say fetch 2 bytes and put them in the 16-bit register. So this gets you the W, which is the value. Remember this list of pointers that gets that pointer, which points at the code field address. That we're going to do is fetch what's at W, boom, 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 into DE. Okay. And that gets us our code address. We're going to exchange so that we can then jump to the code and leaving a register pointing at the word that's executing. So we can have many words that are all, I am a variable and it contains data, or I am a constant and it contains data, or I am a colon word and here's my data, or, and so on. Anyway, that's the thing. It's basically 2 trips through memory to get to the next code to execute. And it ends up being pretty compact. So let's look at a couple of fourth words. I know this is off the end of the normal session. We're just basically reviewing where we want to go and why this is important. So here's a typical fourth word. It's got a name, in this case LIT, and we have marked the beginning and end of it so we can find it. We have a word that says end of dictionary. We have a word that says the code to execute is, and it's right here. So lit is just this code, and lit does something. And what lit does is it says this initial list of pointers to code, the next one isn't a pointer to code, it's actually a value that I want to push on the stack. So we do the right thing. LDAX B inks move, LDAX B inks move, and push it. At the end, we're jumping to next. We're actually jumping to some code just before next that says we want to push H and L onto the stack. So we're pushing something onto the stack. Push DE, push H, LDAX. And it's only 1 byte. Interesting. Really? I think this is a bug. Do I have a bug in my assembly code copy of Fig4th 8080? Because we get L and H here. We go to H push, which only pushes 8 bits onto the stack. Oh, never mind. Push pushes 2 bytes. Idiot me. I am so used to seeing push HL for pushing the register pair that it's crazy. So push H pushes, H push will push 1 word onto the stack from HL. D push pushes 2 words on the stack from DE and HL. DE first, so HL goes on the top of the stack. And then we do this next thing. So all of that means that most of our words get to be very compact. Let's go down to where we actually use colon. Let's take emit as an example. Here's what it looks like in source code, so we don't have all this spread out stuff. We have the encoding of the name, which is basically length and the ASCII name, and then you set the bit on the last bit, so you can find the name going back and forth by looking for the most significant bits. So the links, the dictionary link links back to Inkel -10, which links to here. So these dictionary links are linking back to the beginning of the name field, not the end, which means it's very easy to loop back and find, here's the name, here's the name, here's the name. But it means that if we have headless words, which you could do words that don't have a name field. It does mean that you need to have a byte that says there's no name here. So if I were redesigning the way words worked in Figforth, I would have had this link here, linked not to the beginning of the name, but actually linked to this word in the previous thing. So this would be just linked to Enkel. So we would be the address of the code field of the preceding word, not the name field. Anyway, so emit, we've got the head. Actually, you can discard this whole thing if you don't need the dictionary links. If you don't have a name, you don't need dictionary links. So this whole thing for headless code, this goes away. So emit says, I have a colon word. I would do emit, one out, p store semis. And in fourth, that is p emit, one out t, store semi s. So the way we'd write that in fourth would look something like this. If I can be so bold. Colon emit is p emit, one out t star semicolon. So p emit is being called first. P emit is some code which prints a character to the console. It's in assembly code. So this will pop a character off the stack and send it out to the console. And then we're storing one into out t. Oops, this is p store. Sorry, so we're incrementing out t by 1 and returning. So emit does a p emit and bumps out t by 1. Nothing earth shattering, but it does come fairly close to being optimal. So one out TP store semi S is like LDA something 3 bytes. Increment STA 3 more bytes. So it's 7 bytes, whereas we're doing this in like 6. 1, 2, 3, 4, 5, 6. Yeah, so it's not truly compressing it much at this point. Here's a longer one. This is the colon word itself. Oh, let's not look at this. This is all meta stuff. So traverse, all these words, they start to get kind of big. It's easy to look at the fourth source code because for assembly code, there are some words we can't use. I can't use these all have to be legal labels in assembly code. And the fourth word's going to have things like dash dupe. Anyway, so the difference between a fourth that fits in RAM and a fourth that fits in ROM is if the fourth is in ROM, if the words are in ROM, then the parameter field can't be changed. Now, mostly that's okay. But the difference comes if you have a variable. And in fourth, a var looks like this. So I say I have a name, and my code field pointer points to do var, and following that is the place where we're storing it. So we can't put a var in ROM, or we won't be able to change it. We can, however, do, if we want to have a variable, we set it up as a constant, and the value of the constant is the address we're allocating. So we need to have, in our ROM fourth, we need to have it know where its variables are stored so that it can allocate memory to store variables. So when you declare a var to go into the ROM, it actually declares a con and gives it an address in memory. So all of these places where we say do var will have to be updated to do the right thing. Now, it may very well be that we modify do var or we keep var in place. The idea would be that you would have the ROM, we'd have the fourth in ROM, and if you define any new words, they go down in RAM. Anyway, so there's our target, which is that we have a ROM monitor from which we can boot CPM, or we can drop into fourth. And long term, if I can write the fourth so it doesn't require CPM, okay, then we can have the boot ROM boot directly into fourth. And the way you do that is you put your BIOS in ROM. Okay, so here's the BIOS. So the question is, do I want to run CPM 1.4 or 2.2 or 3.x? If I'm running 2.0 or better, I need to start adding more things to CBIOS. And if I'm going to run CPM 3, I need to go find the CBIOS stuff for CPM 3. And I don't have that on hand yet. So we have some stuff here which is common. There's actually a standard CBIOS, and all of this wboot and load stuff. This is all just well done code that will work for booting CPM up from a mass storage controller. It knows the number of sectors that CPM requires, so you can actually boot CPM from a diskette that has more sectors on it than CPM expects, but you do expect to have the right number of sectors on the track. And it does this by calling the entry points. So we actually call set track and set sec and set DMA and so on. In the case of DMA, when we do the read and the write, we're not going to be triggering the controller to do DMA. We're going to be loading all this data into the controller, and we will be doing the DMA to the address for the sector. So these content TBDs, this is our disk read and write operations. We also need to fill in console status, console in, console out, list output, punch output, reader input. Those are all content TBDs that we need to fill into the CBIOS. Once we've done that, I am fairly certain that Figforth uses the BIOS for all of its I/O. So if we have a copy of the CPM BIOS in ROM, we can execute it from there. Or if we have a copy of the CPM BIOS relocated for its appropriate location in RAM, the boot ROM can copy it into place, okay, without touching mass storage. It can copy the BIOS from ROM into the appropriate location and trigger Figforth to run. Worst case, what we do is we just put the image of Figforth in the ROMs. Now, Figforth itself stretches from 100 hex here. So here's where we start. And it will take up all the way down to here, 1B75 hex. Which is 7,000. So we have about 8. If we fit in 8 kilobytes, we could take this image and put it in 8 kilobytes of ROM, which is 4 ROMs for us. And what we would do is when we boot, we would just copy Figforth down into memory at the appropriate address. So load Figforth into memory, we'll load the BIOS into memory, and start Figforth running. And now we have Figforth running with the BIOS, not having had to boot CPM. And I think that's going to be our initial system. And once we have Figforth running, then if Figforth terminates by diving into the CBIOS at the appropriate address. So remember, if we jump here into CBIOS cold start, this is going to load CPM from the disk, isn't it? Okay, so we're going to cheat. We're going to have our hard reset, load these into appropriate places in memory and run them. And only if Forth decides to terminate to CPM do we attempt to load CPM from the A drive or other drive if we write the Forth code to do that. So this gets us our fourth prom. reason why I like fourth proms. Remember, I mentioned that I worked at Sun. So we used fourth in our boot ROMs. And it wasn't just because we thought it might be cool to have a different language and maybe we wanted to be renegades. The fact is that fourth is a REPL, read, execute, print loop, that allows you to do operations, not just math. I can say, read this memory byte, write this memory byte, scan this area of memory, look for this. So think about what happens when you are turning on a piece of computer hardware for the first time in the lab. You've got a CPU board that's going to start executing, and you're going to want a ROM monitor where you can examine memory and print it, where you can write data to memory, where you can write something and read it back and make sure you got the right stuff. A fourth available to you means that you can do all sorts of things. It turns the computer you're bringing up into a tool for bringing up the computer you're bringing up. This saved us so much time. The 4600 series, for example, which was our first multiprocessor, the day we turned it on in the lab with the real hardware for the first time, we had already gotten the port working because we were able to run the simulated system with the boot ROMs, with the boot ROM images that we would later use to bring up the real hardware, and get some fourth code working inside the simulation that did the right thing, including fourth code that would boot Unix. Think about that for a second. If you have fourth code that reads from your disk controller, reads from the simulation of the disk controller, and the simulation is good enough, you drop it in the real system, it's now reading the real disk controller. Well, you now have a fourth word that says read this sector. And you read it, and it's a boot sector. And what the boot sector do is calling back into your fourth ROM to read the rest of the boot. And then you've got the boot program, which calls back into the fourth ROM to read parts of the disk, to look at a file system, to read Unix. So before this, there was a program called /boot that Sun had, which was fairly big because it had to have drivers for all the possible devices. Well, the fourth ROMs for any given computer that we produced had drivers for the particular storage that would plug into it. And the theory of the S-Bus was that if you produced a new S-Bus card, which was a controller for a new disk, it would contain, listen carefully, the fourth code for the drivers for itself. And if you're writing in fourth, the binary image that you write, if you do it carefully enough, does not have anything CPU specific. So you could write fourth code that would work on a 386, on a Spark, on a Motorola 68000, and so on, as long as they all have the same fourth interpreter, and all the machine code comes from the original fourth ROM. So you plug it into your disk controller, it carries enough of, not a great driver, but enough of a driver for you to boot. So the /boot program suddenly lost all of these drivers. Boom, it got smaller. /boot became a text file, which was less than a kilobyte. And it could then load in VM Unix and start it running. So we had all this debugged. And we were able to start the real system and get into the fourth monitor and poke at it, make sure it's working, read some disk sectors, make sure we got the right data, and then let her rip. And literally between getting our final chip at the docking set, so it wasn't, when Chuck said, hey, I've got the chip all loaded into the board, we're ready to power on, it was from the moment the last chip appeared in the dock at Sun, less than 24 hours later, this machine was up and running and on the Ethernet and was sending mail to the officers at Sun. So our CEO got mail less than 24 hours after the chip arrived that the computer was up and running Unix. Wasn't bug-free. We still had some debugging to do, but it was running, which means we were 99% of the way there. So that's why I like fourth in ROM. That's why we're going this direction. So we need 8 kilobytes to store the fourth image. We need a couple of kilobytes to store the BIOS image, which is like overkill. M size times 20. I'm not sure how big the BIOS gets. It's actually a fairly small thing. I'm sure that the image I had up here of CPM showed how many sectors it takes up, but it's fairly small. Like I said, I only need to implement a few things here. So image of the BIOS, which we can then write to the appropriate location, image of fig4th, write to the appropriate location, and jump to it, and we are done. So between sessions, I'm going to go off and I'm going to write some of that code. And when we come back, we will start thinking about configuring up our first actual computer, which will be able to talk. Let's see if I can get my TTY displaying here. Printing terminal, come on, where are you? There you go, and let's get you mapped onto the screen properly. Where'd it go? There we go. So we should be able to start interacting on this nice yellow teletype with fig4th, assuming I've got a good image of fig4th. Now there's a lot of OCR that goes on in this stuff. So let's call it here. I'm going to go off and do some background information, and when we come back, we'll start building a computer out of all of these parts, because I think we have all the parts we need to build one. I will talk to you soon. And until then, keep it small, keep it fast, and keep it